Good day, welcome to Group 29's presentation on fluid compressibility for MECA in 2024A. In this presentation, we will be analyzing the generalized compressibility chart of gases. The figure illustrated is called the generalized compressibility chart. The graph illustrates the compressibility factor Z, which is on the vertical axis, the reduced pressure PR on the horizontal axis, and the reduced temperature TR. The compressibility factor Z is unitless and is measured using the form Z is equal to PV over RT, where P is the pressure, V the specific volume, R the specific gas constant, and T is the temperature of the measured gas. PR and TR are dimensionless variables. PR represents the reduced pressure and is calculated using the equation PR is equal to P over PC, where PR is inversely proportional to PC. PC is the critical pressure of the gas, and P is the pressure of the gas being calculated, both measured in bar or kilopascals. TR represents the reduced temperature and is calculated using TR is equal to T over Tc, where T is the temperature of the gas measured in Kelvin, and the Tc is the critical temperature of the gas, measured in Kelvin. The values of Pc and Tc are obtained from Table A1 in the thermodynamic property tables from the Principles of Engineering Thermodynamics textbook.
The solid lines representing TR values are obtained by drawing a line of best fit through the experimental data collected on the tested hydrocarbons. From the chart, we see that with increasing pressure, there is more deviation of the values of reduced temperature. Looking at the reduced temperature lines, as Z and PR increases, the slope or gradient of the TR lines decreases. On the graph, it is observed that as Z approaches 1 at fixed reduced temperature, the reduced pressure tends towards 0. While the pressure P is small relative to the critical pressure, it is assumed that the compressibility factor Z is approximately equal to the value 1. Using the prior statement, we can assume that when the substance has Z equals 1, the substance is an ideal gas. The ideal gas assumption is illustrated in the diagram shown as a piston cylinder assembly. The gas is compressible. We will now take a look at the following example to illustrate how to use the chart to solve problems. 3.5 kg of propane in a rigid tank at 4000 kilopascals at 110 degrees Celsius is heated to 130 degrees Celsius. Determine the initial volume in the tank in meter cubed using data from the compressibility chart.
We will first list the known information, which is mass, pressure, initial and final temperature. Since we're required to find the initial volume, we'll use the initial temperature in our calculations. Secondly, we convert the temperature from degrees Celsius to Kelvin and pressure from kilopascals to bar. The next step is to look at the thermodynamic table A1 to find the critical temperature, critical pressure, and molar mass of propane. We then calculate the reduced pressure and reduced temperature as shown, as well as finding the specific gas constant for propane. Using the discovered PR and TR values, we determine the compressibility factor Z for propane from the compressibility chart. We then plug in the calculated variables into the compressibility formula in order to determine the specific volume. Finally, the volume in the tank is calculated by multiplying the mass, the specific volume, and getting the answer in cubic meters. An alternative approach is the initial volume can be calculated solely using thermodynamic tables. From table A18, we determine the specific volume at 40 bar and 383.15 Kelvin and use the formula volume is equals to specific volume multiplied by mass in order to obtain the volume. The initial volume calculated using thermodynamic tables results in a 17% error from the value calculated using the compressibility chart.